Right, now we're going to look at a situation where I have a torque, but it's not in static equilibrium. So what that's going to cause is it's going to cause this disk I have here to angularly accelerate. And I want to figure out what is the angular acceleration caused by a 5 Newton tension applied to the outside edge. So you can imagine I have like a light string wrapped around this disk, and I'm going to pull on that light string with a force of 5 newtons. What's the angular acceleration? So I set up my problem just like we did before in static equilibrium, but now we're going to sum up the torques, and it's going to equal I alpha. So I have my 5 newtons. It's at a radius of 20 centimeters, and so I will have to change this to 0.2 meters because we need meters. You'll notice that my lever arm and my force are perpendicular, and we need to decide, is this going to cause a clockwise or a counterclockwise? Looking at it is going to cause a clockwise torque, so it's going to be negative. And so I have a negative 5 times its distance, 0.2, is equal to I. Now the moment of inertia is something you're going to have to look up on the table. Your table looks something like this sheet here. It's on the back of your green sheet. And so I can look up for a uniform disk. It's going to be an I value of 1/2 mr squared times alpha. And so now I just need to go ahead and solve for alpha. The mass of the disk is 5. The radius is 0.2. And so I have negative 5 times 0.2 equals 1/2 times 5 times 0.2 squared. You'll notice some things cancel for me. So my 5's cancel. I lose a 0.2. And so I have my alpha still over here. So I'm going to move these over to the other side. And so I have half of 0.2 is 0.1. So divided over, I get negative 10 radians per second squared will be my alpha value.